Okay. Oh, sorry. That was loud even for me. Alright, we're doing a daily problem, 19th of March, 2026. Alright, another submatrix question. Who would have thought? Count the submatrices with equal frequency of x and y. Given a 2D matrix grid with grid of I, j being either x, y, or a dot. Okay. Return the number of submatrices that contain zeros, grid of zeros. Okay, so that kind of anchoring idea is still there from yesterday. So take the top left element, an equal number of x's and y's, and at least one x, and therefore at least one y. Fine. So, for example, if you have something like this, you notice that you have an x at the very start, which means you need a y as well, exactly one y. So you go like there, you can go like there. You can even take that one because it's a dot. But if you try to take the 2 by 2, or the entire matrix, you'll have 2 y's, 1 x. It doesn't count. So you have an output of 3. Very nice. Here is a problem because it would look like, so for that second example, what have I done? For the second example, it's x, 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 y. So it would be like x, 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 y. It's fairly clear that no matter what you do, you're always going to have too many x's and not enough y's, right? So you'll either have just the 1x by itself, you're going to have 2 x's, you're going to have 2 x's, or you're going to have 3 x's and 1 y. So you never satisfy the conditions, output is 0. Here you don't even have an x to begin with, so you're definitely not going to satisfy that condition, and therefore you won't satisfy that one. Yeah, okay. And then we have 1,000 by 1,000, so there'll be like about 1,000,000 elements in the worst case in the matrix, and then yeah, you got that. Okay. This isn't, I don't know, like it's obviously there's some similarities between this and yesterday's problem, but what was yesterday's problem? It was like I was so proud of solving it, now I've forgotten. It was about you have a binary matrix, and you have to figure out how many submatrices. The sum. All the submatrices that sum less than or equal to k. I wonder if you can do something similar. If I change all the x's to 1s, all the y's to -1s, all of the dots to 0s, then if the sum is equal to 0, if the sum of the submatrix is equal to 0, that indicates there's an equal number of x's and y's, is there not? The only extra check is I have to make sure there is exactly, at least, I think we can transform this. I think this is almost a modification of yesterday's problem. The only issue is, for example, that last problem, where it's all zeros, all the submatrices would add up to 0, right? But I have to make sure that there is at least one x. I do like this. I guess it would have to be a copy, because I'd be like significantly changing the size. For every 1 byte or 2 bytes, I guess, for strings, would become 4 bytes for an integer. But I do like it. It's a nice idea, especially since it's motivated by yesterday's problem. 1, -1, 0. -1, 0, 0. And then you basically apply the same algorithm that we did yesterday with the k equals to... but instead of being less than k, it has to be exactly equal to k, where k is equal to 0. So that would be my idea. Yeah, okay. So I'll just write the title 3212. So POTD 3212. The basic plan would be x's become 1s, y's become -1s, and the dots become 0. I guess, yeah. And then, what am I trying to say? From there, let the target sum equal 0, and then basically say you know, do that row prefix sum, and then the col prefix sum. So from the original, you pass it through that, and then you pass it through that, and then you should get basically a matrix where if I call this guy equal to capital C, C of a particular row in a particular column tells you the sum of elements in the submatrix, sort of starting at C's M, where M is the original, M00, and ending at C, sorry, M, RC. So like, I'm just writing out what I've already said, basically. I can do an example. So x, y, y, and then dot, dot, dot. So x, y, y, and then dot, dot, and dot. That's a y. So the transformation would look like +1, -1, -1, 0, 0, 0. What the row prefix process, so this is like the row prefix process, would do is it figures out the cumulative sum along each row. So it starts, so for the first row it would be 1, and then the cumulative sum would be 0, and then with another 0 makes 0. Then the cumulative sum for the second row would be -1, and then still -1, and then still -1, because you're adding 0, then adding 0. Then you do a similar idea, but with the columns, using this guy as the input. So you have, for the first column, 1, and then cumulative sum means it goes down to 0. This is 0, and then with the cumulative sum goes down to -1. And then with the 0 and the -1, you got 0 and then -1, right? So this is the kind of final thing I'm looking at. And then basically all I would have to do in this particular case is look for all the zeros. Because, for example, if I focus on this 0, this is telling me that if I take the original matrix and look at these two elements, look at the submatrix formed by the top left and the highlighted cell, then this should satisfy the condition, and it does, right? X and Y. Same thing with the bottom guy down here. This should also satisfy the condition, X and Y. And finally, over here, this also satisfies the condition, right? Now, the issue though is that right now I have no detection. I have no way of detecting if I've actually seen a 1 at all, right? What I think I can do though is what I'm basically going to be doing is looking for all the zeros, right? So I can just traverse like this, like, you know, for each row, and then within each row, go through each column. If I see a 1 or a -1 while, you know, traversing along, then I know that I've seen an X or a Y, right? So like I've seen an X here, so I set a flag to true, like we definitely have an X. The only issue is you don't really have, you need to make sure you keep track of, okay, let me make a new example just so I can like explain myself. So I need some kind of way of keeping track of whether I've seen an X or a Y. That's like the goal. If I have something like X, well, maybe I won't do an X straight away. Maybe I'll do like a dot, and another dot, and another dot. I'll do like X, Y, Y, X, 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 1, 2, 3, 4. Y, Y, Y. 1, 2, 3, 4. Let me put an X here as well. Right? So by our same kind of process, we would transform this into a numerical array. So 0, 0, +1, positive 1, negative 1, negative 1, positive 1, all ones, and then all negatives. Then we do our prefix stuff. So this is the row prefix. So this is the mapping. This is the row prefix, which would be 0, 0, positive 1, 1, 0, negative 1, 1, 2, 3, and then negative 1, negative 2, negative 3. Then we do the col prefix thingy, column prefix, 2, 3, 4. You have 0, 1, 2, 1. You have 0, 0, 2, 0. You have 1, 0, 3, 0. Okay, so I think we're gonna have to work with M, the original, and this final matrix in tandem. Like, I might just copy it. I might just copy this guy. Because on top of like looking for all the zeros in the final, looking for all the zeros in the final C matrix, this guy, we're also going to need to make sure we actually have seen a y or a negative y, a y or an x in the original M. So this is C and this is M. So I guess like we have pointers that point to a particular position, right? Like R and little c. And then we, at the same time, will have a corresponding set of, like, will be the same indices pointing to M. And so we say, hey, look, we saw a C, we saw a 0 in the C matrix. So this could be what we want. But we need to be able to feel like, say, hey, actually, we haven't seen an X or a Y yet. We've only seen, a dot. Same kind of thing here. We say, look, there's a 0, but it doesn't work. Then we see a 1, so that's not going to do anything. What I will say though is once you see the 1 in capital M, you know that once you've done that, then you know that from here, so if I label the indices 0, 1, and 2, for all matrices with column greater than or equal to 2, we have seen an X, basically, right? So for this matrix, there we know there's an X. For this matrix, we know there's an X. If the matrix was bigger, like this, for example, then we'd know that there's an X in there, right? Because the column surpasses 2. Although row needs to be at least 0. So I think, okay, this might be really dumb. Oh, it's like not that dumb, but it's a little bit dumb. I want to have like another matrix. Which basically is like a Boolean matrix, purely keeping track of whether or not a particular submatrix will have a 1 or a 0. So, for example, this should be false, this should be false. We know there's a 1, so we set this to true. Now, this is a 1, this is a 1, and this is a... I need to put more zeros. Hang on. Oh, no. I've made the example bad. I should have put more zeros. I should have put more dots. Let's say... let's say there's a couple of dots like here and here, here and here. Maybe a dot here. Okay, so it's I think we're taking like a dynamic programming approach. Basically, so there's a 0, this would be a 0, and these 4 would be zeros, right? So what did I say? 0 over there and then 4 zeros. So this is a 0 and these 4 zeros. Right. So false, false, true, and then let me get rid of U. So to just, even though there's a 0 here, right? Of course this should be false because this matrix alone is not able to, this matrix does not have any ones or negative ones in it. But to actually decide if it's a 0, we can't just look at this individual value. We have to look at I think I have to look at the value above and the value to the left. Because the value above tells me if I've seen a 1 or negative 1 in this kind of matrix. And the value left tells me if I've seen a 1 or a 0 in this kind of matrix. So I think if I call this B for Boolean, the Boolean of RC is equal to the Boolean of R minus 1, C minus 1, and Boolean at, no, wait, this is wrong. What am I doing? R minus 1, C, so up, and then same row, but C minus 1 to the left. I don't know, this is more intuitive than actual thinking, but let me work at a better example. I think for now we'll just say this is false, and we'll keep working through it, and then hopefully it'll make more sense. And then this is definitely true because it's a negative one. This is definitely true because it's a negative one. This is true because there's a positive one, you know for sure. Now, if we focus on this next 0 over here, maybe I'll do it in a different color, green. This should say true, right? Because this matrix has a negative 1 in it, has a 1 and a negative 1 in it, right? Obviously, it's not necessarily obvious when you look just at that 0, but because there was a value over here and a value over here, you know for sure that those values will be included when you add this sort of matrix. You know what I mean? When you add this spot to, when you sort of are considering this spot, you're considering this entire matrix. So the only way there can be a negative 1 in this matrix is if there was a negative 1 in, this is getting really bad. The only way there can be a non-zero, only way okay, let me argue this one more time. Only way you can know that that you've seen an X or Y at this point is either there's an X or Y in here, or you would have seen an X and Y in the above matrix, sort of here, or you've seen an X or Y in the left matrix over here, which is told. So if M at RC is not 0, then B at RC is equal to true, right? Else, I think it makes sense to say B of RC, else B of RC is equal to, look at the value above if possible, right? It should be or, not and. Or look at the value to the left. And that should tell you whether or not you've seen a 1 or negative, an X or a Y at this point in green. So then this will be set to true. Now let's just say for argument's sake that this was actually a 0, right? It was a dot here, in which case this would be false because we haven't seen anything yet. This would still be set to true because you've seen the 1 there. You know what I mean? This 1, or this true, is telling you that somewhere from sort of the matrix from the top left down to that value, somewhere there is a 1, which means if you kind of take this matrix, you'll still have that 1, wherever it is. In this case, it is here, but we don't know that, right? And so I think, yeah, if you apply the same idea here for this 0, this is true, so ORing it will make true. For -1, you know it's true straight away. For 0, even though it's a 0, to the left and above it, there's a true. And then this will also be true because you look at that. So I believe you actually don't need yeah, okay. And then from there, now I can actually traverse my C matrix, remember this guy, and basically every time I see a 0, I check if I've seen an X or Y yet. So these two zeros won't be counted because these are false. But this 0, oh wait, I made this, this was meant to be, wait. Yeah, okay, this should be fine. Did I change this to a dot? Was this originally, this was originally a Y, but I made this 0. Okay, hopefully it makes sense. I think this will work. So I'm going to create a Boolean matrix out of, so I'm going to do the mapping first, then create the Boolean matrix, then make the R and C matrix, and then hopefully good things happen. Let's find out. So the B matrix, no, the M matrix first, equals, maybe I'll make it the dimensions first. So the number of rows is equal to length of grid. And in fact, I hate using M. Num rows equals the length of grid. Cols is equal to length of grid at the first row. That tells you number of columns. And then we're going to create the B matrix, which is like seen X yet, or seen X yet, seen XY yet, is equal to, we'll say false for in range num cols, and we're making that many rows for in range num rows. So seen XY yet. So we've done that, and then we're going to make the M matrix, the mapping matrix, which is, we'll just set it to zeros. 0 for in range num cols, for in range num rows. Okay, so then for I need the indices, don't I? For R in range num rows, for C in range num cols. If I can actually do both of these together, can't I? If grid at RC is equal to X, then, or is equal to dot, say X, then mapping at this R and C is equal to 1. Elif grid at RC is equal to Y. I can also say seen XY yet at RC is equal to what did I say? It's a true, right? Mapping at RC is equal to 1. Seen XY yet at RC is also equal to true, naturally. Else, which means we've seen a dot, no need to change mapping because it's already set to 0. So what did I say? In the else case, the seen XY yet at RC is equal to seen XY yet at R minus 1C, or seen XY yet RC minus 1. Now, there are naturally going to be some index problems, so if R will have to be at least 1. So I need the variables, I think. Scene xy above equals false. And then scene xy above is equal to this guy in the above row, right? And then scene xy to the left is equal to false. If c is at least 1, then scene xy left is equal to this guy. And then we OR the variables instead of the thing. Okay, hopefully that is accurate. I hope this is going well. So we've basically done all that initialization. Now I have to do the... I will do this in separate steps like last time because I don't want to... Why is my zooming... Oh, there we go. I'll do this in separate steps because I don't want to doubt myself. Okay, so the row prefix... I can do this... Ooh, see, now that I've handled the Boolean, I think I can do this in place for the scene, for the mapping, right? It's like the matrix variable from yesterday. Mapping for R in range num rows, for C in range num cols. No, wait. I can do this smart. I don't need, if I'm going across the rows, I can start columns at 1 because the 0th column isn't going to change for row prefix. Mapping at this row, this column adds on the mapping same row but previous column. And that should do the row prefix. And then for C in range num cols, for R in range num rows, but starting at 1, right? Mapping at, did I put 3 P's? I did. Mapping at RC adds on mapping at the previous row, but same column. So this is the bit where we're going like from M, the mapping, to R, to C, like this is the process that I'm taking. And then finally, for R in range num cols, I need a counter. For R in range num cols, for C in range, whoa, this is wrong, num rows, for C in range num cols, if mapping at RC is equal to 0 and scene xy yet at RC is true, then answer plus equals 1. And then return the answer. Oh man, is this correct? Who knows? I think I back the general idea. I just don't know if... I think this relationship makes sense. It's like, because looking at the guy above tells you if you've seen an XY in like that above matrix, you know? So if red is like, I tried to draw something and I grabbed a real pen, not my stylus, that was a bit stupid. So if I'm trying to figure out, you know, have I seen an X or Y yet in the red matrix? Well, I can look. Maybe I'll do a different matrix. I think the red one's a bit too squished to the border. Oh, everything's gone. It's fine. It's good enough. I can reconstruct it. Okay. So this was my matrix. So, like, for example, if my goal is to say, have I seen an XY yet in this matrix? In this red matrix, then that's the same thing as asking, have I seen an X or Y yet in this matrix? Or have I seen X and Y in this black matrix? If I have seen an X or Y in either of these places, then I will definitely see an X or Y in the red matrix. You know? That's my logic, and that's why I believe this should work for setting scene X, the scene XY matrix. So we've got scene XY is false everywhere, mapping is 0 everywhere. If we see X, then the mapping becomes 1. Scene is true. If it's Y, oh, -1. Mapping becomes -1, seen becomes true as well, else seen becomes false. If there is something above you, yeah, then you're able to check, we're able to check that green matrix. You can, otherwise seen x, if there's nothing above you, then of course seen xy above should be false, right? Because there's nothing above you to check. Seen xy left, same deal, is false. If there is a column to the left of you, then check that column. Same row, but check that column. And then seen xy yet, that's the B matrix, that's this thing we're constructing. Seen xy yet at RC, I have made the variables very similar to each other. Seen xy yet at RC is seen xy above, and that's all within the else. That's all within here. Okay, so I think I backed the mapping, and I think I backed like the original mapping, and I think I backed the seen xy yet. Then yeah, this is the same as before, like yesterday. So for each row, for each column, do a prefix sum. For each column, for each row, do the prefix sum down the columns, right? So for each column, like we're going down the column, adding the previous row on, yeah. And then we do this, and this should be right. All right, let's just try this. See if there's any major issues. Okay, good. I should do more testing, really, because I think there's enough wriggle room for me to make errors. The good news is I did return 0 here, which is good. It passed that case, which means I'll just chuck in the example I drew up. So x x. What was it? .yy dot y and then x x and then y . No comma. Ugh, so much punctuation. I don't think this is helpful at all. Thought it would be, but now I'm not sure. Yeah. And then y . Okay. Okay. I mean, we'll do small cases. What is the smallest it can get? It can get 1 by 1. So like, what if I just have like dot, Good. Same thing with like the x. Good. Okay. I think so long as this is -1, then I think everything should be handled as expected. Fingers crossed. Yay! Ooh, I'm better than the mode. I don't know if I can claim that, to be fair. Although what I would imagine is being faster would mean handling the for loops maybe in one go. Like maybe you could do all of this in one go. I was thinking about that in yesterday's problem, but I didn't get it right, so I didn't bother. I think maybe how you get slower would be like if you do the mapping and the seen xy thing separately. Like I was handling them in one go, but you could, I guess, reiterate if you wanted. Let's see what. I mean, there was a spike of people who. What the heck is that? Okay, there's a spike of people who did very well. Oh wow, he even wrote full-on documentation. Overall, this would take, given the modest constraints, generated the 2D prefix, along the two symbols in question, incrementing some counter when the two non-zero frequencies met. Yes, overall this would take O of mn time with O of nm or O of m additional space if you keep all the frequencies or the bare base minimum. Version 1.1, reduce the number of additions by calculating both frequencies simultaneously by letting one of the units be sufficiently large enough to avoid any collisions/overlaps. Wow, he used NumPy. That's all you need to know, right? Yeah, wow, fair enough. I guess units is a Is it like like a is it like a table but like you can with like headings kind of thing? Is that what this is? I don't think I've seen this before. 90. Okay. Um units is units. Yeah, this is kind of crazy. Fair enough. Is there anyone who like did normal stuff? Okay, there you go. Oh wow. Wait, this is legal? You can add boolean to whatever this is number. Does it cast to one and zero? One and what? Like do boolean? I guess yeah, that makes sense actually. Do languages generally do that? I think they do. Can't remember. Wait, you only take the number of columns? You don't even need the number of rows? Oh, because you don't. Okay, fair enough. That's very impressive. So you have two lists, I guess indicating how many. I guess it's how many X's you've seen in that in like up to this column maybe. But like every time you go down a row, you re-update the same column. Like rather than like having a completely different spot to put the number in, you just overwrite the previous number is what I'm guessing. For row in grid, row X, row Y is 0. Row X, row Y. Okay. For J in range, so for all the columns, row X, you add on the fact that is this current value an X? And you add 1 if it is, and you add 0 if it's not. Row Y, you row J is equal to Y. You add on if it's a Y or not. X at J plus equals row X. Y at J is plus equal row Y. So you're saying after you've updated okay. So you're like every time you're going down the column, you update X at that column with the number of X's you saw or maybe didn't see. Is that right? So row X is telling you how many X's are in that row. So X of J, adding on the number you saw in that row onto X of J tells you how many. I don't know if I get it. Answer plus equals X of J being greater than 0. So this is checking if you've seen an X yet and checking so it's like a way of keeping track of the frequencies and how many X's you've seen. It's very good. I don't know. I'm just not really clicking right now. All right, well, it's not bad. What I did. I mean, it made sense. Very well. Very motivated by what I saw yesterday. Yeah, okay. I kind of forgot. I think yeah, the mapping thing. I guess I didn't really need because you could cast booleans into integers, so that's quite cool. But yeah, fair enough. All right. I'm assuming this is like kind of what I did. I assume. Yeah. There you go. Mapping and then using a hash table is smart actually. Yeah. That's an interesting variable name. All right. Well, I don't know. I guess I could look into this again. Maybe I mean, I have it recorded, so I'll look at it at a different time. But right now, I don't think it's gonna click because I need to work. I think I have to work through the code properly. All right. Very good.